Today I'm going to talk about my experiences using Mathematica for text and image mining in my own research. Scholarship in the humanities, including history, differs from science and engineering along a number of dimensions. First, there's a focus on close reading and interpretation of sources. These include things like texts, images, artifacts, and media. If humanities researchers are going to use powerful computational tools in their own research, tailored to their own research, typically they have to develop those tools on their own. The first project that I'll mention was one of the largest that I've been involved with. The Old Bailey Online is a fully searchable edition of all of the criminal trials that were held at London's Central Criminal Court between 1674 and 1913. The figure that you see in this slide shows the length of a criminal trial in words on the y-axis, plotted against the date of the trial on the x-axis. The murders in this archive are depicted with a red dot, and all of the other trials are depicted with a lighter, more translucent gray dot. And in fact, most of the trials in the archive, the majority of the trials in this archive, are actually thefts. Now, one of the things that's interesting about this graph is you'll notice that the trial length starts to bifurcate in the 1800s, with some trials being less than about 100 words in length, and some of them more than a couple of hundred words in length, but there are relatively few in between, so there's a split in trial length. Now, this pattern of behavior persists over more than 50 years, and until we plotted the data in this form, no one had actually noticed that it was there or had observed that it was there. And it reflects a number of factors, but among other things, it reflects the rise of plea bargaining in the 19th century and the rise of the guilty plea. Let me turn to a project that's just getting started, and this is one that's more typical of my research collaborations. I'm working with one other person, Amy Bell, and she's an expert on mid-20th century British cultural history. She's an expert on the subject matter, the time and the place, and I'm handling the programming and the methods more generally for our project. The subject of our research in this case is the Mass Observation Project. In 1937, the Mass Observation Organization began recruiting hundreds of volunteers to write diaries and to answer questionnaires. And they also paid investigators to do things like go into public situations and just write down people's conversations and descriptions of their behaviors. And the goal of the project was to better understand the lives of ordinary Britons. And this project resulted in an extensive archive of the daily life and culture of mid-20th century Britain. We're working with a method called distributional concept analysis, which was developed by Peter Debola and his colleagues. And whereas many text analysis methods rely on n-gram windows that are centered on a word of interest, the DCA method is interesting because it relies on small n-gram windows that are positioned some distance before and after the word of interest. Another project that I worked on for many years that involved text and image mining was conducted with a former student of mine. He and I applied a number of techniques to the subject of stage magic in the late 19th and early 20th century. And what we were trying to do is we were trying to develop a kind of an experimental approach to history. So we used techniques like desktop fabrication and physical computing, but we also did a lot of text and image mining. We had a fairly large collection of periodicals, books, and in a number of cases, entire runs of magic magazines. And part of the work involved automatically and extracting images from those page images, and then identifying the things in them, people, apparatus, card tricks, and so on. The picture here from that project shows some of the now problematic Orientalist costumes that magicians of the time preferred to wear. Here's another example of images from that same work. There's a collection at the University of Manitoba that contains seance photography from the early 20th century. And some of these images are actually stereoscopic pairs. With a few lines of code, it's possible to create a wobble image that alternates left and right frames rapidly. Another collaborative project that I've been working on for a number of years also involves text and image mining. For this project, I started by using Mathematica to write crawlers to compile an archive of millions of pages of text from the open web. And the kind of thing that I was collecting were texts that relate to the histories of electronics, of computation, and of scientific instrumentation. One focus of this work has been developing tools that can understand circuit diagrams. These images show the automated labeling of components in a circuit image. So this image was extracted automatically from the surrounding text, and then we then go through and use machine vision techniques and that kind of thing to automatically label and identify components. Underneath the labeled schematic, you can see the network that shows the ways that those components are connected to one another. And our ultimate aim in this work is to develop a system that can identify meaningful assemblies of components, meaningful design idioms, if you will, that occur in schematics above the level of individual components. So when we think about being able to do semantic search for the history of electronics, we want to be able to search for design idioms, things like a Wheatstone bridge, for example, and not for just to be able to search for a particular resistor, a particular capacitor, which isn't nearly as useful. As a final example, I'll mention another project in the history of engineering that we just started. My collaborator here is a retired professor of civil engineering. We're creating a large database of historical bridge images with a lot of metadata. We have about 4,000 images right now, but the number is growing daily. And we're combining these records in our database with linked open data via Mathematica's new support for Sparkle queries. And we're developing a machine vision system to go along with it. The idea is to be able to create a system that can look at historical bridge images and can extract features that are of interest in the history of civil engineering. And we hope to be able to use machine vision and image processing techniques to really bring out that aspect of these particular sources. Any source that contains links to other sources can be crawled. The canonical example, of course, is web crawling. Now, in this case, what I'm showing is a crawl of very limited crawl of the WorldCat Identities API. This is a 2-hop crawl of related records around the mid-20th century author Walter Lippmann. The Identities site gives access to about 20 million records, metadata, for persons, institutions, fictional characters, and things like that that are mentioned in published sources or that published sources are about. Now, of course, Mathematica also provides a very rich collection of tools for categorizing nodes or characterizing nodes, vertices, networks. So we can use all of those tools on anything that we crawl. And we can also resolve entities, like Walter Lippmann himself, to entities in Mathematica's entity framework. And we can resolve them to entities in sources of linked open data, like Wikidata. And this provides us a tremendous access to still more computable knowledge. When we have texts, which we've gathered by crawling or other means, we can make connections between those texts, and we can make things in those texts findable by way of indexing. In this slide, I'm showing an example of a method called RAKE, Rapid Automatic Keyword Extraction, and I'm using it on the Wikipedia article for information overload. Now, Rake is an excellent way to extract phrasal keywords, particularly in shorter texts like abstracts and summaries. And if we combine it with more traditional methods, some of which Mathematica is now implementing, like TF-IDF, we have a good way of assessing the relevance of a particular text to a particular query. And we also have a good way of measuring the similarity between pairs of texts. If we combine this with entity recognition, especially in the form of Mathematica's pretty amazing text contents command and its relatives, we can link keywords that we find, that we extract either through TF-IDF or through Rake, to entities. We can also use keywords as a very useful form for discovery. So I find, since I often work with large collections of sources that have been kind of curated by me intentionally, I find I'll often have a question, a research question, and the answer is actually in my sources, and the keywords lead me to the location of what I'm looking for. I've often already collected the answer to questions that I'm just coming up with. This particular slide shows a compression clustering algorithm that was developed by Rudy Celebresi and Paul Vitagni. It's based on Kolmogorov complexity, but in a form that can be implemented on a computer. And it is used here on the biographies of various people who were important in early Canadian history. And it shows us relationships between those people. If you know these people or these this time, you'll recognize some of these people in the relationships. Now, I often use quick clustering algorithms like this one for discovery while I'm writing. So I can write a paragraph about something, and then I can use a clustering algorithm to cluster the paragraph that I've just written with all of my sources. And the sources that best match that paragraph are typically the ones that I want to cite if I haven't cited them already. For this kind of application, if you're clustering your own writing with your source base to look for more ideas, more linkages that you hadn't perhaps thought of, or more references that are useful for you, it makes sense to burst your documents into smaller units. And again, it's the matter of a line or two of code in Mathematica to burst a document into paragraphs or pages or 250 or 500 word text blocks, or whatever is useful for your application. One fast technique for mining things like terminology, or for getting a sense of the semantic characteristics of your texts, is the random indexing method of Magnus Solgren and his colleagues. Now, like a number of useful methods, this one creates vectors of co-occurrence events that occur in a context window around a particular word. It's based on random vectors, which means that the dimensionality of the space never increases. So this is very fast, and it scales well to really large text collections. And again, it's easy enough to implement in a page or two of code. The example here shows left and right contexts of two words in Alice in Wonderland, said and replied. And what it shows us is that Lewis Carroll preferred to use the phrase said Alice instead of Alice said, but he preferred to write Alice replied instead of replied Alice. So by looking at the left context of replied and the right context of said, we can see that those terms are the ones that are most likely to be found in front of or behind those particular verbs. Now, random indexing can also be used to find words that pattern together. So we find in Alice in Wonderland that in the places where we find the word Alice, we would also find, in similar environments, we also find words like king, caterpillar, pigeon, and so on. Solgren and his colleagues show how to use random indexing to measure the semantic density of words. They show how to use this technique to study semantic evolution over time and how to monitor ongoing discourse for anomalies.